All right. So in the world of databases, there's this constant tug of war happening. On one side, you've got this drive for perfect, spotless data organization. I mean, everything in its right place. But on the other side, you have the never-ending need for speed. And what we're going to dig into is how these two things, organization and speed, are often in a head-to-head battle.
And that leads us right to the big question for today. Why is it that when we get our data perfectly neat and tidy, our apps can sometimes just slow to a crawl? I know, it sounds completely backward, right? Well, stick with me, because the answer to this is all about a really crucial balancing act that's at the core of all good database design. Okay, so before we can start organizing anything, we first need to understand the mess we're dealing with. And in a badly structured database, we're not just talking about a little bit of clutter. No, we're facing something way more sinister, a world of what are called data anomalies. So, what exactly is a data anomaly? Think of it like a glitch in the matrix of your data. It's this totally unexpected, weird side effect that pops up when you're trying to do something super simple, like adding, changing, or deleting information. And trust me, these aren't just little bugs we're talking about. These things can completely corrupt your entire database. This chaos really breaks down into three main types. First up, you have an insertion anomaly. Imagine this. You try to add a new professor to your system, but you can't because they haven't been assigned a course yet. The system just won't let you. Then there's the update anomaly. This one's a classic. A professor moves, so you go to update their address. But you have to change it in like 10 different places. You miss one, and boom. Now the database thinks they live in two places at once. And finally, the one that gives people nightmares, the deletion anomaly. You delete a course that's no longer offered, and you accidentally wipe out the professor's entire record right along with it. Yikes. So, how do we fight back against all this chaos? Well, the first and most classic solution is a process called normalization. You can think of it as the Marie Kondo method for your database. It's this amazing, systematic way to declutter everything and bring order and integrity back to your data. At its heart, normalization is all about one thing: killing redundancy. See, instead of storing the same piece of info over and over and over again, the idea is you store it in exactly one place. And the way you do that is by breaking down these giant, clunky tables into smaller, much more focused ones, and then you just link them together. This is what makes sure your data stays logical, consistent, and way, way easier to manage. Now, this whole normalization thing happens in stages, and we call them normal forms. The first one, 1NF, is super basic. Every single cell in your table gets its own single value. That's it. Think of it like making sure there's only one item in each little box on a spreadsheet. Easy enough. Then 2NF makes sure that everything in a row is actually about the main subject of that row. No freeloaders. And finally, 3NF does one last sweep, making sure that secondary details aren't depending on other secondary details. Each step is just a deeper and deeper level of cleanup. And you can really see that journey right here in this diagram. You start with this unorganized mess, right? The first step is just getting everything into its own little box. That's your 1NF. Then, the next step groups all the related data together, which gets you to 2NF. And that final step, it just tidies up any last little dependencies, leaving you with this beautiful, clean, logically structured database in 3NF. It's a perfect example of that progressive tidying up process. So, you might be asking, what's the big payoff for all this work? Well, it's all about flexibility. As this quote from Wikipedia points out, when your database is fully normalized, you can add new kinds of data later on without having to completely rip apart your existing structure. Essentially, you've future-proofed your database. It's built to grow and evolve. Okay, so everything's perfect, right? We've cleaned up the mess, our data is pristine, we've reached data utopia. But, and you knew there was a but coming, our story takes a twist. It turns out that all this perfection, it comes at a price. And that price can be summed up in just one word: joins. You see, by splitting our data into all of those perfectly neat, separate little tables, we've accidentally created a brand new problem. To get a complete picture of anything, we now have to stitch all that information back together again. So a join is basically the operation that reconnects those tables we so carefully separated. For example, if you want a customer's name and what they ordered, you have to join the customers table with the orders table. Now, look, if you only have a handful of records, that's no big deal. But what if you have millions of customers and millions of orders? Suddenly, doing those joins becomes a really heavy task for the computer. In fact, they can become the single biggest bottleneck that slows your entire application down. And this is where our second solution comes in. And I gotta warn you, at first this is gonna sound like total heresy. It's called denormalization. But this isn't about being messy or lazy, not at all. It's about taking a very strategic, very calculated shortcut to get our speed back. Denormalization is the process of intentionally adding some of that redundancy we worked so hard to get rid of back into the database. And the goal is super simple: make reading data faster. By putting some of that related information back into the same table, we can avoid those slow, expensive joins when we just need to pull up some information, which, let's be honest, is what most apps are doing most of the time. And there's a whole bag of tricks for how to do this. You can do things like add redundant columns back in, like storing the customer's name right in the orders table, so you don't need to do a join just for that. You can also pre-calculate values that are expensive to figure out on the fly, or create totally separate summary tables. It's all about picking the right shortcut to solve your specific speed problem. Here's a really practical example of how this plays out. Sometimes denormalization is as simple as making a conscious decision not to normalize your database all the way to the end. For apps that do a ton of data reading, think about things like analytics platforms or big reporting dashboards, just stopping at the second normal form can be a fantastic compromise. It gives you a little bit of organization without sacrificing all of your speed. So there you have it. We've got these two powerful opposing forces. On one side, we have normalization, our champion of data integrity. And on the other, we have denormalization, our champion of pure speed. And the real resolution here isn't that one is good and the other is bad. The answer is that it's a classic engineering trade-off. It is, as the title says, a balancing act. And this table really lays out those trade-offs beautifully. Look at normalization. Its goal is integrity, it's faster for writing data, and it saves on space. This makes it perfect for write-heavy applications, like an online store's checkout system where new orders are constantly being created. Then you've got denormalization. Its goal is performance. It's way faster for reading data, but it uses more space, and you have to be careful about inconsistencies. This makes it a no-brainer for read-heavy applications, like that analytics dashboard we talked about. So really, the key takeaway here is this: there is no single best way to do things. It is all about using the right tool for the right job. I mean, you wouldn't use a sledgehammer to put a screw in the wall, right? The choice between normalization and denormalization boils down to one simple question: what does your application do most of the time? Is it writing a ton of new data, or is it reading a ton of existing data? Your answer to that question tells you which path to take. And that really leaves us with one final thought to chew on. The next time you're looking at a database system, or maybe even designing a new one, you have to ask yourself this critical question: is this thing built for perfect textbook integrity, or is it built for practical, real-world speed? Because finding that perfect balance between the two, well, that's the true art of database design.